Next, we look at selection sort. It also grows a sorted prefix, but it decides what enters that prefix in a very different way. Selection sort also builds a sorted prefix, but it picks the next element in a different way. It scans the whole remaining part for the smallest value, then swaps that smallest value into place. One pass works like this. We scan A from index I to index n-1 and find the smallest value. We swap it into position I, which is one swap per pass, not one swap per comparison. The prefix A from index 0 to index I-1 then grows by exactly 1, and it is guaranteed smallest first. Watch out for one thing. The scan for the minimum never takes a shortcut. It always inspects every remaining element, even when the array is already sorted. That is why selection sort has no best case that beats its worst case. Let's read selection sort in pseudocode. The outer loop runs I from 0 up to n-2. We start by guessing that the minimum is at index I, so we set min to I. The inner loop runs j from I plus 1 to n-1, scanning the whole unsorted part. If A at index j is less than A at index min, we found a smaller value, so we update min to j after the scan. If min is not equal to I, we exchange O at index I with A at index min, that is one swap per pass. Notice the inner loop always runs all the way to the end. It cannot stop early, unlike insertion sort's shift loop, which stops as soon as the key fits. Let's sort the array 5, 2, 9, 1, 5, 6. We watch pass 0's scan in full. The green cell is the smallest value found so far. It starts at index 0, value 5. Now we scan the rest for anything smaller. The J marker moves to index 1. The value there is 2, which is less than 5. So 2 is the new smallest, shown in green. The old cell goes plain again. J moves to index 2. The value is 9. 9 is not smaller than 2, so the smallest stays at index 1. The scan does not stop early. J moves to index 3. The value is 1, which is less than 2, so 1 is the new smallest in green. J moves to index 4. The value is 5. 5 is not smaller than 1, so the smallest stays at index 3. J moves to index 5, the last cell. The value is 6, still not smaller than 1. The scan is done. We looked at every cell, no shortcut. The smallest is 1 at index 3. Now one swap. We swap index 0 and index 3. The smallest value, 1, moves to the front and locks in indigo. One swap for the whole pass. The sorted prefix is 1. Pass 1 summarized. The scan again looks at all the rest and finds 2 already in place, so there is no swap. The sorted prefix grows to 1 too. Pass 2. The smallest of the rest is 5. It swaps into index 2 and locks. The sorted prefix is 1, 2, 5. Pass 3. The smallest of the rest is the other 5. It swaps in and locks. The sorted prefix is 1, 2, 5, 5. Pass 4. The smallest of the rest is 6. It swaps in and locks. The last cell is sorted by elimination. The sorted prefix is 1, 2, 5, 5, 6. Done. The whole array is indigo and sorted. 1, 2, 5, 5, 6, 9. At most one swap per pass, and some passes do 0. Here is selection sort in C. The outer loop walks I across the array. Each pass fills position I with the right value. We start by assuming the minimum is at I itself. Then the inner loop scans everything after I. Whenever we find something smaller, we remember its index. After the scan, if the minimum was somewhere else, we swap it into position. I notice this is one swap per pass, no matter how far the minimum had to travel. That is selection sort's one real advantage. It makes at most n-1 swaps. Predict then reveal. Insertion sort drops to big O of n on already sorted input. So predict. Does giving selection sort a sorted array make it any faster? Pause and answer. The answer is no. The inner scan still has to inspect every remaining element on every pass, just to confirm which one is smallest. So best, average, and worst case are all big O of n squared. That is the exact opposite of insertion sort, and it is why the word adaptive matters. Let's sum up selection sort's cost. Its best, average, and worst case are all the same big O of n squared, because the minimum finding scan never takes a shortcut. It is not stable because a faraway minimum can leap over an equal element on its way to the front. It is in place, and it has one real advantage. It does at most n swaps in total, which helps when writing to memory is expensive. Plain numbers hide instability. Two identical 5s look the same wherever they end up. So we tag the two 5s as 5A and 5B. They share the same sort key, but we can tell them apart. The top row is the start, 5A, 3, 5B, 1. First pass, I equals 0. We scan by key only. The smallest key is 1 at index 3. We swap it into index 0, the amber cell. The front now holds 1. Look what that swap did to 5A. The 1 came from index 3. So 5A was thrown all the way to the back, into index 3. That is the amber cell on the right. In the input, 5A came before 5B. Now it sits behind it. Second pass, I equals 1. The smallest key in the rest is already 3 at index 1, so there is no swap. The amber cell just marks that 3 stays. Third pass, I equals 2. Now A at index 2 is 5B and A at index 3 is 5A. Their keys are equal, so A at index J is less than A at index min is false, and min stays at index 2. No swap. The final array is 1, 3, 5B, 5A. This table makes it plain. In the input, 5A was at index 0 and 5B was at index 2, so 5A came first. In the output, 5A moved to index 3 and 5B stayed at index 2, so 5B comes first. The tied keys came out reordered. Let us define the word. A sort is stable if equal keys keep their original input order. Look back at what just happened. Selection sort's very first swap put the faraway minimum 1, where 5A was, which pushed 5A past 5B. So equal keys can come out reordered. Selection sort is not stable. Merge sort's merge step breaks ties with less than or equal, which keeps equal keys in their original order. That one operator is the whole difference.